Hello again. I just got a fright. I didn't want to have to record everything all over again. And what I'm looking at on the screen to monitor what's going on up here is backwards. And I thought, you know what? I could say I did that on purpose to challenge my students, but I don't think I'm going to do that. It is recording it left to right order correctly, thank goodness. So here we are. Threw me off track. But now we've got this sorted list that starts with 5 and goes all the way through 5,000. But we got here in a somewhat painful way in that almost all of the left, here's the description again. Almost all of the left gets merged, gets copied down. Then the last element is 5,000 right here. We got stuck. That's larger than any of the right. So now we got to start comparisons on the right-hand side. 65, 67, all that stuff. So everybody gets compared to one of the other numbers. Very few. The 5,000 is the only one that we get to copy down for free. Now, this was, of course, not the entire sorting algorithm. This is just the very bottom. That's the very last merge that we do back together. The question becomes then, over here, since we're analyzing this, I'll switch colors. What is this? Purple? Purple's a good analytical color. Question, just as we did with bubble sort, I hope that shows up as a little different color. How many comparisons? And I think I'll just answer it over here in the picture rather than trying to describe it, because that description didn't work out terribly well, did it? Even though it's correct, it just doesn't make any sense. Let's see. Every one of these, 5, 12, 13, yada, 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 up to 42. Every one of those, no, up to 45 was compared to 65. So to get how far? To get this far, that took n over 2 minus 1. The size of this half is n over 2. The size of the whole thing is n. The size of this half is n over 2. And if I compare 5 through 45, then I did, for this part, n over 2 minus 1, because we didn't make it all the way to the 5,000. n minus 1 over, no. Caffeine just doesn't do the trick as well as it did earlier in the module. Pity me, won't you? N over 2 would be the entire tray. N over 2 minus 1 is all we had to do to get up through 45 down here, because when we run into the 5,000, it doesn't go in the bottom tray. Now, what about this? This right-hand half here, 65, 67. You know what? We copied that entire. This is not a circle. It's a blob. But to get this blob down here, every single thing in the right-hand side got compared to the 5,000. The 5,000 was the only one that got a free trip down to the big tray at the bottom. How many comparisons over here? Well, you know what? The size of the right-hand half over here is also capital N over 2. So this is a full-blown N over 2 comparisons in a big, solid purple box. So, in this worst case, pushed out to extreme, we did n over 2 comparisons to get this first half in order and n over 2 comparisons in the second half. And you'll notice I left off the minus 1 for huge values of n. If this were a list of 1,000,000 items, that minus 1 is just pittance. It doesn't make any difference at all. So I'm going to say approximately, A-P-P-R-O-X. I can't spell it. I should have said about. It's too late now. Approximately n over 2 plus, that's the left-hand side, plus n over 2 for the right-hand side. Comparisons. Comps for comparisons. Oh no, fractions. I think I can add those two. If I've got half n and add those together, I get a whole n. Approximately, then, instead of n over 2, n comparisons. And you think, wow, that is great. Merge sort is going to be an order in algorithm. And you'd be wrong. Because remember, this is only the very last thing. This is the grand finale of merge sort. This is after we did all that other stuff and all those different colors in the previous example. This is just the last iteration, getting this last tray in order. Now, since I've already had to split videos and keep going, I think I'll keep going on this one. But think about that. It took n comparisons just to get to this last level. to get the two bigger halves, the two biggest halves, merged back together into one whole thing. Okay, how fast can I erase the board? Depends on how fast I can find my eraser. Let's abstract away the numbers and assume that we have adequately analyzed. No wonder I couldn't say those two words together. Adequately analyzed the worst case for that one iteration, which is let's do all the comparisons we need to do. Fortunately, all we got to do is analyze how many comparisons are done below the bottom line of that first example, the dotted line, because that's the only place where any work's being done. But if this is size n, if our list is size n, then we just got through determining with a specific example of the worst case that to get this put in place and get this put in place, it's going to take about a comparison per element, about n over 2 comparisons over here and about n over 2 comparisons over here. Okay? I hope you can read that. How did merge sort get to the point where it could even do that last step? Well, remember, it splits in half, splits in half. I'm having a flashback of the cat and the hat comes back. One of those cats takes the hat off, it's got another one, takes the hat off, it just keeps going and going and going. Well, merge sort, to get this in order, it had to split that in half. This is blue, which is not different enough from black, but you just have to take my word for it. So how many comparisons did it take at this iteration to get these two halves into that 1/2 size piece? Well, each of these pieces is n over 4 in length, n over 4. So to merge those, it took one comparison per element, roughly. Almost exactly, but roughly one comparison per element. So to get these merged, it's going to take n over 4 plus n over 4 comparisons. Same thing over here. N over 4 for half of this half, n over 4 for the other half of this half, about a comparison per element for each of those halves, will get us to this point. Now, I don't know how long this list is. If this is 812, I don't want to keep doing this on the board. I will use a better color this time. How did we get this blue list in order? We called the merge sort recursively, and it split this in half, which we're now down to look at this. N over 8. N over 8 and n over 8 are the sizes of the two halves of an n over 4 list. And as quickly as I can, whoops, I'm going to kick the board out of range of the camera. I'll do that. And I'll also do this arrow and that, and that, and that. And yes, it's dot time, finally and mercifully. I don't know how many times I can split it, but each time I split it, I get two lists that are half the size of each list at the previous level. Now watch this. This was an easy addition. To add that up, we had n over 2 plus n over 2 comparisons for a grand total of going from the last two big halves to the final whole list. It took a grand total of n comparisons. Why? Because n over 2 plus n over 2 is n, for crying out loud. N over 2 comparisons to put this down here, n over 2 comparisons to put that down here, grand total of n. What about this? Well, to get these two in here, it's going to be n over 4 comparisons plus n over 4 for a grand total of n over 2 comparisons. But wait, the other blue lists over here, these are all the same length, all the blue lists. They're also going to take n over 4 plus n over 4. Look at that. I could even do that math in my head. If I've got 4 n over 4s and I add them up, you know what? I'm going to get n comparisons. Ruh-roh. Rapidly we see a pattern developing. I hope so. Through the glare on the board. Sorry about that. What about this? Well, it takes about a comparison per element. And how many different little lists of size n over 8 do we have? 1, 2, 3, 4, 5, 6, 7, 8. Add all those up. N over 8 plus n over 8 8 times is going to be n comparisons. Dot, dot, dot. Until we can split in half no more because we're down to single elements. So, what does that tell us? It's trying to tell us something. I know it is. is trying to say from each level, going from the smaller list to the next larger list size, all of those smaller lists, all the comparisons added together is going to be in the number of things in the original list. Same thing all the way down to where, this is actually upside down, isn't it? To where the lists are nothing but single elements. So in comparisons times, here we've got to do some math. Drum roll. Order in the number of comparisons it takes to get one row to the next row times however many rows we have. How many rows do we have? Let's see. Split in half once, split in half again, split in half again. N times the number of times. Capital N can be split in half. Let me read that back. You know what? That's going to get a highlight. That actually is the order of magnitude of merge sort in the worst case. What is actually the order of magnitude? The order of magnitude is not order n, like best case bubble sort. It's not order n squared, like worst case bubble sort. No, no. It is order n times the number of times n can be split in half. That's not a very succinct way to express it, unfortunately. So we need to work on this. This is correct. It's just not very compact. And for that reason, it's not acceptable. We're not going to leave it like that. We will take care of that in the next video. Actually, I think I'm going to write this up here and start the next video that way. Erase the board. I won't drag you through my erasing the board. I'll see you online.